In this lecture, I present 3 tests on the combustion of gasoline in a one-cylinder engine. Test 1 deals with the combustion of gasoline with a standard ignition. Test 2 and 3 deal with the combustion of gasoline in the same one-cylinder engine, but equipped with hyper-combustion of hadronic mechanics at a progressively increasing energy rate, but without, I repeat, without any nuclear contribution. By assuming a knowledge from the references of the preceding lecture on our achievement of the full combustion of a gaseous fossil fuel at Magna Gas Corporation, I then show that the combustion of gaseous and liquid fossil fuel in a 1 and 4 cylinder engine with hypercombustion without nuclear contribution appears, I repeat, appears to meet the requirement by the US Environmental Protection Agency for the free release of their exhaust gases without catalytic converter. By contrast, the clean combustion of coal and other solid fuel used in home heating and in the production of electricity require the design and construction of a new form of hyperignition which is capable of triggering the radiation-free hyperfusions of hadronic mechanics. In the event confirmed, this result will imply the lack of release of harmful contaminants in the atmosphere, as well as a conversion into a useful form of energy which is generally lost in contaminants during combustions. In plain terms, the combustion of combustible contaminant in fossil fuel exhaust is equivalent to a reduction of their cost. In viewing the 3 tests, I suggest to focus the attention in the wavefront, the operating voltage, and the data of the 5-way exhaust analyzer. We are now ready to compare the exhaust data collected by our five-way gas analyzer of test 3 with the EPA limits of exhaust gases for the combustion of gasoline in one-cylinder engines. The first table summarizes the results of test 1, 2, and 3. Please take some time to read the numerical data. The main result reported in the line below the table is that our hypercombustion for test 3, despite its use at the minimum of 200 volts, has caused a truly major reduction of combustible contaminants in the exhaust, since carbon monoxide is reduced by 83%. I repeat, carbon monoxide is reduced by 83%, while hydrocarbons are reduced by 73%. Hydrocarbon reduced by 73%, by therefore offering realistic possibility that our hypercombustion may meet EPA limits for the release of exhaust gases in the atmosphere without catalytic converter. In the second table, I provided EPA limits for one-cylinder engine and their units, while in the third table, I provide comparison with measured exhaust data of test 3 and their unit. As one can see, EPA limits are expressed in terms of grams per kilowatt hour, while the data of test 3 have been measured in parts per million. The conversion of the latter units into the former require various additional measurements that are currently underway. Consequently, as shown in the first table of this new slide, the compliance of test 3 with the EPA requirements cannot, I repeat, cannot be formally stated at this writing. Nevertheless, estimates done by our engineer show that test 3 data are indeed favorable for meeting EPA requirement for reasons listed in the second table, where one can see that carbon monoxide is far below the EPA limits, while hydrocarbons and NOx are very close to said limit, resulting in a high possibility that the EPA requirements could be met. Nevertheless, one should keep in mind that our hypercombustion was operated in test 3 with the variac at the minimum of 200 volts. The expectation is therefore that EPA requirements may also be met or surpassed for hypercombustion when it is operated at a bigger power. In conclusion, the exhaust data of test 3 may indeed verify EPA emission requirements for the production and sale of gasoline-operated one-cylinder engine releasing exhaust gas in our atmosphere without a catalytic converter when equipped with hypercombustion of hadronic mechanics operating at a minimum of 200 volts. This slide illustrates that the transition from one to four-cylinder engine is quite simple for our hypercombustion, because it was conceived ab initio to have one hyper-ignition per cylinder. Therefore, the transition from one to four-cylinder engine may require 3 more hyper-ignition units. We now compare exhaust data collected by our five-way gas analyzer for test 3 with EPA limits of exhaust gas for 4-cylinder engine. In the first table, I provided a representative value of exhaust gases of gasoline combustion in recent 4-cylinder engine prior to catalytic converter. Recall that in the transition from 1 to 4-cylinder engine, there is a significant improvement in the gasoline combustion due to the replacement of inefficient mechanical carburetor with highly efficient electronic fuel injection and consequential decrease of the contaminants in the exhaust. Despite that, we are cautiously assume that 4-cylinder engine with hyperignition generates the same exhaust contaminant as those of 1-cylinder engine. That is, CO is 0.16%, hydrocarbon 853 parts per million, CO2 11%, NOx 0 parts per million, O2 6.6%. In this case, the extrapolation of hyperignition from test 3 to a modern 4-cylinder gasoline engine predicts the substantial reduction of exhaust contaminant presented in the box at the end of the slide. For instance, carbon monoxide is predicted to be reduced from 5,000 parts per million to 833 parts per million, hydrocarbon from 300 to 81 parts per million, and so on. The projected 4-cylinder exhaust contaminants for the combustion of gasoline in a fuel-injected 4-cylinder engine with the same hyperignition as that of test 3 are presented at the top table, and they have a clear possibility of meeting EPA requirement illustrated in the second table. In conclusion, it appears that the combustion of gasoline in a modern 4-cylinder engine equipped with the same hypercombustion adopted for the 1-cylinder engine may indeed meet EPA requirement for release in the atmosphere without catalytic converter. More generally, our tests indicated that the use of hyperignition without nuclear synthesis appears to be sufficient to achieve full combustion of gaseous or liquid fossil fuels. By contrast, hyperignition with radiation-free nuclear synthesis, such as Santilli hyperfusions, appears to be necessary for the achievement of full combustion of coal and other solid fossil fuel used in home heating, in electrical power plant, and many other applications. In regard to the emission of carbon dioxide, CO2, which is not currently regulated by governmental agency, my view is that, subject to cooperative academia, petroleum company, and governmental agency, CO2 emitted in fossil fuel combustion should be one day collected in pressure bottles and recycled via a ionization process such as those permitted by the hadronic reactors into fullerene, oxygen, and ozone. In my capacities as Chief Scientist of Hadronic Technology Corporation, this slide is to testify that following the completion of this lecture and subject to independent confirmation, the research laboratory of our company has conducted additional tests presented in the following video on the combustion of gasoline in the one-cylinder engine equipped with the same hypercombustion used in test 2 and 3, but with the following new spark parameter. With systematic achievement of the following new exhaust data. That, to my best knowledge, constituted the first known achievement of complete combustion of gasoline in an internal combustion engine, that is, combustion without combustible contaminants in the exhaust, and therefore without any detectable carbon monoxide and hydrocarbon in the exhaust. Thank you for your attention.